So what I want to do next is I want to take a topic that you've probably seen before and then shed a little bit of new light on it. I want to look at it in a new way. So I think this will be particularly helpful for kind of deepening our understanding of this idea. So this idea that we're going to talk about is a zero of a function and what it means to talk about the multiplicity of it. And then kind of the flip side of that when we're dividing by, when we have a, f over g and then g has zeros of particular order. So we'll talk about kind of the reverse scenario later. But if you have a function f that's holomorphic on a region G, remember holomorphic now we know is synonymous with analytic. So that means that there's a power series representation, namely a Taylor series representation of f. So let's say f is holomorphic over a region. We pick up point C in the region, and then we can write f as a Taylor series centered at C. It's got some radius of convergence. So the picture you should have in your head is that G is going to be some, potato-shaped region here, and then C is inside. And then if f is holomorphic on G, then what you can do is basically find the largest open disk centered at C, and then you can, on that disk, talk about a Taylor series. Okay, so we're implicitly talking about some open disk centered at C. Okay, but what we want to do is we want to study what happens when f of C is 0. And so it turns out when f of C is 0, there's basically two options. Let me get rid of my bad drawing here. There's basically two options. The first option is that all of the derivatives are 0. Okay, so there are two options. So the first option is that f of C is 0, of course. The derivative of f is 0. The second derivative is 0, and so on. Okay, I don't know why I'm writing this funny here. And what that means is that f of z, so and this continues for all derivatives. So if this is true, let me just explain a little bit more here. So what I'm saying is that the first option is that all the derivatives of f at c are 0, okay, for all n greater than or equal to 0. So in this case, what's going on here is just that f is literally the 0 function, at least on that smaller disk centered at C. Okay, so in this case, f of z is 0 in some open disk centered at C. Again, I don't care how small it is, I don't care, whatever. So that's the first possibility, is that all the derivatives of f are 0, in which case f is the 0 function. If f is not the 0 function, then what's going to happen is that f of c is 0, maybe f prime of c is 0, up to a certain point, say the n minus first derivative will be 0, but the nth derivative is not 0. So if it's not true that all the derivatives are 0 for all n, there's got to be some first value where the derivative, the nth derivative at c, is not 0. Okay, so let's say that that first value happens at n. Okay, what that means is that, so in this case, what that means is that we can write f of z as z minus z naught, z minus c to the n times g of z, okay, where g of c is not equal to 0 and where g of z is analytic or holomorphic over that open disk centered at C of whatever radius, over that neighborhood of C. Okay, so that's the second scenario. And notice that if this is the case, what's going to happen is that we have, let me go back to our picture here. So we had some point C, we had some whatever crazy region, I forget what, doesn't matter. And then we had our open disk centered at C. Okay. The zeros here are going to be just at C. You can't have a 0 that's going to be arbitrarily close to C. They have to be separated a little bit. Okay. In other words, the zeros have to be isolated. So if you have a situation where the function f is not identically 0, what that forces is that means that the zeros of the function must be isolated. Okay, so just note that C is an isolated 0. And I forgot one more important thing here. Let me actually just move this note down. So it's important that they're isolated, but we'll come back to that. In this case, if we can write f of z like this, so z minus e to the n times g of z, where g is not 0 at c and where g is holomorphic, we say that, so we say f has, so we say, let me say this a little better. We say that c is a 0 of order n, okay, of f. Okay, so it's a 0 of f, and that 0 has order n. The order, and by order, I'm sorry, wrong word, of multiplicity n. So of multiplicity, I can't spell, multiplicity. Okay, so that multiplicity just means that's how many times it's a 0. In other words, that's how many times you can factor out a z minus c from f. Okay, and so not really anything too, too enlightening here. But if I were to take a function, let's just take something like z minus 3 to the 4th, z plus 1 to the 5th, all over z to the 10th, then 3 is a 0 of f of multiplicity 4. Okay, that's basically all that this is saying here. And then the rest of this function is going to be some function that over some neighborhoods, over some disk centered at 3, but excluding 3, it's going to be, over some disk centered at 3, it's going to be analytic there. So if I look at the rest of this, this is going to be non-zero and holomorphic over some neighborhood centered at 3. So that's really all I wanted to say about multiplicity. So you can really get a little bit of a better handle on this, thinking about this in terms of Taylor series. So it turns out that zeros of functions are either going to be isolated in the sense that when I say isolated, remember what that means is that you can find an open disk that contains only that 0. So there's, maybe some other places where the function is going to be 0, but you can always separate them by like little open disk neighborhoods. Okay, you can always isolate them in that sense. Okay, so that's what isolated means here. Okay, so that's zeros and multiplicities of functions.